How big is the biggest rocky planet? Could you have a planet made of iron? Why is the moon floating away while Mars's moon is falling down? All this and more in this week's question show. Hey everyone, welcome to the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops into your brain, just write it down in the YouTube comments and then I will gather a bunch of them up here and I will answer them. But also, we do this show live every Monday at 5 p.m. Pacific time. So if you want to get follow-on questions, if you want to chat with the other members of the community, go ahead and join the show every Monday at 5 p.m. Pacific time. I will have an event somewhere around here on my channel, and so you should definitely go and click on the notification bell so that you will be reminded when the show is going to go live. All right, let's get into the questions. Sin 6 Grim Reaper. Jupiter is a gaseous planet. What would the size of the biggest rocky planet be, excluding hydrogen and helium? So the biggest rocky planet that astronomers have discovered so far is a planet called TOI 849b. And there is a bunch of information in there that'll tell you it is a TESS observation. So it was discovered by NASA's TESS satellite. And it is B, so in other words, that is the first planet that is orbiting around the star TOI 849, which probably has another name in another catalog. So the planet has 40 times the mass of the Earth. 40 times, which is crazy. But the planet is 3 times the size of the Earth, and it is a rocky planet, like based on the density measurements that astronomers were able to make, has about 3 times the size of the Earth. And I'm sure you're wondering, like, what would it be like to be a creature that lives on the surface of a world with 40 times the mass of the Earth? And the surface gravity of the planet is about 3.3 times the surface gravity of Earth. And so if you were standing on the surface of this planet with 40 times the mass of the Earth, you would still be experiencing 3.3 times the force of gravity. Like, that would be hard for you to walk around, but not impossible. Like, you could probably crawl around. It would be tricky. How do you get a world with 40 times the mass of the Earth? And so the theory is that this was once a gas giant and it had its outer gaseous layers stripped away by its star. It orbits very close to its star, and all that remains is the rocky core. And it might very well be that many of the larger, more massive rocky planets that we find out there have gone through this same process. Now, I'm sure you've noticed the Star Wars planet code that's popped up above my shoulder, and this is a way for you to vote for the questions that you think are the best in this episode. And the winner, again, by a landslide, was from Jason. What is the theoretical size of a planet? And I guess that was the first one we answered. And so this is great. Actually, as I said, I got a million questions about the sizes of planets. So don't be surprised if we spend a lot of time talking about that in this episode. And then I guess this will be like our new Lagrange point. So anyway, congratulations to Jason. Congratulations to me for the answer. We made a great team. So remember, watch the whole episode. You'll see the planet names. In the end, post the planet name for the one that you thought was the best in the comments down below. We'll add them up and we will celebrate the winner next week. All right, let's move on with the questions. Babymaker. How big could an iron planet get before collapsing into a black hole, given that it wouldn't have active fusion to push out? I would guess that it would be less massive than an equivalent star. All right, so there's a bunch of pieces working together here. The first one is iron, and you correctly noticed that iron doesn't give you fusion. And so this is one of the situations that happens with a star. When you have a very massive star, a star that is many times the mass of the sun, it is fusing material in its core. It starts with fusing hydrogen into helium, and then it has still the kind of pressure to continue up the chain of elements. When it runs out of hydrogen in the core, it starts fusing the helium together, and then it starts fusing carbon and neon, and it works its way all the way up to iron. And when it hits iron, the problem is that iron is not a net positive for the fusion process. It takes about as much energy to fuse iron as it releases. And so all of this radiation pressure that was keeping the star in this big spherical shape goes away almost instantaneously. And then all of the outer layers of the star come crashing down inward, and then you get this sort of compactification at the middle, and you also get this bounce. So you get the black hole or neutron star forming at the middle, then you get all of the energy that's released from the supernova. And so you are taking just the raw iron, the finished product of what would be in the middle of a star that was many times the mass of the sun, and you're wondering what would happen. And so if you started out and just started piling iron up, then it would be no problem. But the mutual gravity of all of that iron would be pulling it down together, closer and closer, getting more and more dense as you kept at it. And if you were about, a little below the mass of the sun, you would end up with a white dwarf that is the mass of a ball of iron, right? A white dwarf, an iron white dwarf. And you could get up to just shy of the Chandrasekhar limit. This is the phase between white dwarfs and neutron stars. And so when you cross this 1.2 to 1.4 times the mass of the sun, now the pressure that's pulling inward against the atomic pressure of the iron that's pushing outward would be overcome, and it would shift into becoming a neutron star. And so you would have the neutrons and the protons getting mashed together, and you would no longer have iron. But this process would also be quite dramatic, because you would get the thing essentially collapsing down and turning into a black hole. But the part that's kind of weird is that normally when you've got this black hole forming, you've got all of this outer envelope of the star. You've got this, 10, 20 times the mass of the star that is coming inward at like 70% the speed of light, that is mashing down the core, and that helps to contribute to both the formation of the black hole as well as the explosion of the supernova. So it might very well be that the thing just kind of winks out of existence, that you don't get the gigantic supernova explosion that you would with a star. And there are objects out there that might be kind of like this. So there's a term that astronomers use called unnova. And the gist is that there was a star there, and now the star is gone. And the assumption is that now it's been replaced with a black hole, but there was no supernova in between. That at one point, the star was just sitting there, and then it ran out of fuel in its core, and then the outer layers collapsed down, and maybe it just, the way the turbulence worked or something, the way the magnetics worked, it didn't get that gigantic supernova explosion. It just all went nicely into the black hole and just turned invisible. And you just go from star to nothing. And it might be that a lot of this happens, that a large percentage of the stars out there that we would think explode as traditional supernova are just disappearing into black holes with no intervening step. So don't do it. Greg Rumscheit. Why is our moon floating away and not going to crash back down, and Mars moons are falling back down? Yeah, the Earth's moon is moving away from us at about 1 centimeter per year. And we know this because when they landed on the moon, the astronauts put down these retroreflectors onto the surface of the moon. And now you can fire a laser beam at the moon. It'll bounce off one of these retroreflectors, come back to you. You know the speed of light. You time how long it takes for the laser pulse to get to the moon and back. And that tells you the distance to the moon. And then you do that experiment 1 year later, and you find that it takes a tiny little bit longer for your laser pulse to get back to you. And you do the math, and you realize that the moon has gone 1 centimeter farther away from us. And this behavior is completely expected. And I mentioned a couple of question shows ago that it's the opposite situation for Phobos at Mars. The moon Phobos orbiting around Mars is getting closer and closer to Mars. And in about 50 million years or so, the gravity of Mars will tear Phobos apart, and then the pieces of Phobos will rain down and crash into Mars. And so the question really is, why is the moon drifting away when Phobos is moving closer? And the answer is the orbital time of the moon compared to the rotation time of the planet. And so in the case of the Earth and the moon, the Earth takes 24 hours to turn once on its axis, and the moon takes about 28 days to orbit around the Earth. And so the tidal interactions between the Earth and the moon is essentially causing a bulge on the Earth, and that is causing the Earth's rotation to slow down. And to sort of conserve the momentum between the Earth-Moon system, the moon slightly shifts outward as this goes. And eventually, over the long period of time, like 50 billion years, the Earth and the moon will lock to each other. And then the Earth will be turning at the exact same rate that the moon is going around it. And then if you're standing on the Earth, you'll be looking up at the moon, and you will always see the moon in the exact same spot in the sky. Now, that'll be after the sun has turned into a red giant and possibly destroyed the inner solar system, but if it all lasts, then that's what you'd see. But with Mars, you've got the opposite situation. So Mars takes about 24 hours, like 24 and a half hours to turn once on its axis, but Phobos takes less than 8 hours to orbit around Mars. And so the opposite situation is happening. The tidal interactions between Phobos are causing Mars to spin up. It's kind of like it's like Phobos has grabbed a handle on Mars and is spinning it faster and faster. And to maintain momentum in the system, the height of Phobos' orbit is coming down, and eventually it will crash. And so whenever you see this situation, if you see a moon orbiting around a planet and the moon is slower than the planet rotation speed, then you know that the moon is going to drift away. And if the moon orbits more quickly than the rotation rate of the planet, then the moon is going to crash eventually. And you'll see this time and time again. And eventually, all things want to lock to each other, like, say, Pluto and Charon, where you've got these two objects, both are tidally locked to each other. Joan Furva. If you're in a spinning spacecraft that simulates gravity and you jump, do you stay floating? No. If you're in a spinning satellite that is mimicking some level of artificial gravity and you are already experiencing an outward force from your rotation around the center of mass from this space station, then you have this outward force that is going to continue on. You jump up and you will jump up for a little bit, and then you will continue back outward, and it'll feel just like jumping, although it'll feel a little different from jumping because of the Coriolis effect. And so when you think about sort of the rotation rate, so you've got the space station is turning, and you're on the outside and you're experiencing, say, 1 gravity for your feet. But if the space station is small enough, then you're going to experience maybe like, say, 90% gravity at your head, which is already going to feel super weird, right? You're going to be experiencing less gravity at your head than you do at your feet. And in some cases, it may make some people sick. And then you jump. And so now your feet are experiencing 90% gravity. And so you will, assuming you can jump your own height, which not many people can, but anyway, then you will kind of drift over a little bit. And so even though if you try to jump exactly straight up and down, you won't land where you took off, but you still will jump up and then come back down and still be on the outside of the space station. But if you were able to somehow like climb a ladder right to the very middle of the station, and then you were able to like push off, then you would be floating in the middle of the station, and you would have the whole station rotating around you. But as you started to drift closer and closer to one of the edges, then you've got this moving mass of air that is turning with the space station, because you're in a sealed space station. And that air will start to speed you up in the way that it's turning, kind of like a wind, and giving you that velocity. And then you will start to drift towards the edge of the station as you're moving faster and faster with the station until you sit down on your feet. Now, I don't know whether like you would fall like really quickly and die, or whether it would just be this very slow drifting. If it's slow and drifting, then that's cool, right? Because you could like enter the station and then you just step off the center of the station and you drift down, float down to the ground, and now you're on the exterior of the station. So I haven't done the math on that, but this is why we need some kind of rotating artificial gravity space station to test out all these ideas, figure out like what is the minimum size where people won't get sick? What is the size that you need to be able to handle the tensile forces that we can build today? What, can you even eat food, pour liquids, play sports games in some kind of rotating cylinder? We don't know the answers to these questions. We need to find them out. So we need to build a giant rotating space station in orbit to test out all these ideas. Please. Kip Nielsen. New SpaceX video was cool. Do you think glass dome cities on Mars are going to be real? I've always thought that subterranean tunnels would be better for the radiation protection. I haven't seen this new SpaceX video that you're talking about, but glass dome cities on Mars. I mean, you don't want to say never, never say never. I mean, who knows what kind of future technology we will develop where we're able to put up glass domes that are strong and sturdy and radiation protectant and can maintain the pressure inside so that people can go out into it. There are a couple of problems. One is the radiation. And so, in fact, there was a fairly recent paper that I had read and reported on Universe Today about how the radiation levels in space, like if it goes through glass, like in a greenhouse at Mars with no radiation protection, is too much for plants. So if you like build a greenhouse on Mars and you try to grow in the greenhouse, then the radiation that's coming from space will kill your plants. And so you can't just grow your plants in sunlight. You need some kind of barrier in between your plants and space. Maybe if you have like a really thick chunk of glass, like something that's like a meter thick, whatever gets you enough protons. But like if you have like a meter thick of glass, will that still let the light shine through nicely? I don't know. So in terms of like growing, chances are we're going to have to grow underground using artificial light, like, big LED grow lights. There's plenty of people with an expertise in this here on Earth, and I'm sure they can adapt that technology to Mars. For the people, same thing. You're going to want to spend a bare minimum amount of time out under glass. And you're going to want to spend most of your time under a meter of rock or more to protect you from the cosmic rays. And so I don't see it being feasible. Like, unless somebody comes up with a kind of glass that is incredibly thick and radiation protective, it's not the kind of risk that people are going to want to take. So, but even just in terms of simplicity, yeah, we're going to go to Mars. The first thing that's going to go to Mars will be a bunch of, I guess, Starship boosters landed on the surface of Mars. And then people are going to dig tunnels underneath the surface, and they're going to live in those tunnels, and that will be their life. Kamui, Master of Disguise. Are we still looking for Planet 9? We are. The existence of Planet 9, some object that is, like, say, the mass of the Earth, maybe even the mass of Uranus, somewhere out beyond the orbit of Pluto, appears to be interacting with the outer solar system. You've got the orbits of all these different Kuiper Belt objects, dwarf planets, way out far away from the sun, and they're moving in such a way that they're being influenced by the gravity of some massive object that is out there. But so far, nobody has been able to find this massive object, and they've looked. And part of the reason is just that the current suite of telescopes just isn't powerful enough and isn't wide-ranging enough to be able to scan all of the places where this thing could be. But good news, there is a powerful new observatory that's coming out in the next couple of years called the Vera Rubin Observatory. And it's going to be an 8+ meter telescope with the largest digital camera ever made. And it will be scanning the entire night sky from the southern hemisphere every couple of nights. And it will find tons of asteroids and comets and supernova. And it'll probably be the telescope that will find Planet 9. So when Vera Rubin comes online and they do a comprehensive search of the night sky in all of the places where Planet 9 could be, and it doesn't find anything, at that point, I think the astronomers are going to need to go back and double check the math, make sure that they are really sure that this thing is out there, because whatever it is, it's going to have to be really small or possibly non-existent. And there are other alternative explanations for how you can get these strange gravitational perturbations to all these objects in the outer solar system. So, Vera Rubin is the machine that will find it. And if it doesn't find it, then there's a pretty good chance that it's not there. Shravan Rowe. As we keep finding more and more dark matter galaxies, would the phrase "there are more galaxies in the universe than there are stars" be true? Well, I think the phrase that you're probably saying is that there are more galaxies in the universe than there are stars in the Milky Way. So the estimate is there are between 100 and 400 billion stars in the Milky Way, and it's estimated that there are about 2 trillion galaxies in the observable universe. And so based on that math, there are more galaxies in the universe than there are stars in the Milky Way. But as you're saying, astronomers are finding more and more of these dark matter galaxies. But that just means there's going to be more galaxies. If we find those additional galaxies that have no stars, but just have a lot of dark matter in them, then there are going to be 2 trillion galaxies, and there's going to be many more, maybe another trillion, that have large amounts of dark matter in them. So no, I think there will always be more galaxies in the observable universe than there are stars in the Milky Way. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep the minimum ads for everybody. Like, as you can see, there are no ads during the video. And as a patron, you'll get an ad-free experience on universetoday.com for life, even if you unsubscribe. You'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Scott Evers, Jimmy Jong, Richard Alton, Chris Ediger, Ishay Oz, John D. Sostrom, Jesper Peterson, George Service, and John Gannon. Join the club at patreon.com/universetoday. Jamie Amendolagine. I'm a longtime lurker and Canadian expat living in California. Do you recommend returning to British Columbia, maybe Vancouver Island, to retire? So for those of you who are watching who don't know, I live on the beautiful island called Vancouver Island on the west coast of Canada in the province of British Columbia. I live about halfway up Vancouver Island in this town called Courtenay. And I actually grew up on an even smaller island, which is just off the coast of Vancouver Island, called Hornby Island. And if you do a search for Hornby Island, people call it the Hawaii of the Gulf Islands, because it has this amazing, giant, powdery, sandy beach that you can go, but it's not warm. I mean, I guess it's warm in the summer when the warm water comes over the sand and heats up. Then it's nice. And it's beautiful here. Like, Vancouver Island, Canada is just gorgeous. For half the year. For half the year, it is rain and cold and pretty miserable. And then around this time of the year, like in early April, everything turns around and the sun comes out and the temperature warms up and the trees get their leaves back and the flowers come out and all the way through. And then the rain goes away. And for the next couple of months, it doesn't rain very often. In fact, we have droughts in the summer. It gets so hot and dry. And it's gorgeous. I love it. I've been in a lot of places in the world, and I'm always kind of going like, would I want to live here compared to living in Canada? And I say no. There's some things very specific places, like, wow, this place has nicer weather than that I'm familiar with. Boy, it sure would be cool to be able to jump in the ocean anytime I wanted, as opposed to only half of the year, and other things. But yeah, you should definitely come back. In fact, like, when you meet people who are Canadians, many of them have come from other parts of Canada, from Eastern Canada, and it's a one-way trip. Like people from Toronto in Eastern Canada, they come out to the West and they don't go back because it's so great out here. I always say that I live in the Florida of Canada, but it's not it's not as warm as Florida, but still, yeah, it's a great place. Lots of trees. People are nice. Kind of expensive, although not too bad if you live in a more rural area. And that's where I met Chad. Here in this city, it's where I met some of the other writers for Universe Today. But yeah, come on back. Marinescu Lucien, do we have a future mission to explore Europa? Yeah, there's 2 missions going to Europa. One is NASA's Europa Clipper mission, which is going to be launching, I think, in 2027. And it's going to fly out to the Jupiter system, and then it's going to make these big, long orbits around Europa. And one of the cool things about the Europa Clipper is it's equipped with a ground-penetrating radar system. So it'll be able to analyze the ice under the surface of Europa, searching for cracks and fissures and under ice lakes. It probably won't see the European space whales, but who knows? So it's a pretty exciting mission, and that's going to really set the groundwork for future missions that will then go. Maybe there'll be a lander to Europa, and eventually there will be a mission that's going to try to melt down through the ice and try and reach the under ice ocean down beneath and really meet the European space whales. And then, of course, the European Space Agency has a mission called JUICE, the Jupiter Icy Moons Explorer, and it's going to be flying past 3 of Jupiter's moons. So it's going to fly past Ganymede, it's going to fly past Europa, and it's going to fly past Callisto. And so it's going to be doing more of an overview of the icy moons, and it's going to end up orbiting Ganymede, which is kind of similar to Europa, like is bigger, has a thick layer of ice, has some kind of liquid ocean underneath, but it also has a magnetosphere, which is very different from any other place. And that is launching in a week from the day that I'm recording this. And so the day that you're watching this, the JUICE mission will be taking off. So it's so funny that you say, like, when are we going to have a mission to explore Europa? Yes. Now there's a mission going to Europa. Elise Nelson, do you know when we will see the next and newest images from Webb? We're getting new images from JWST all the time. Like, every couple of days we're getting new images. The most recent one, as the time that I'm recording this, was a really cool picture of the Cassiopeia A supernova, which is this fairly large cloud of debris that is moving outward ejected from a supernova that happened about 11,000 years ago. And you're seeing this kind of expanding sphere of wreckage in the sky. And we've got many pictures from other telescopes, Hubble, but we got the new images from JWST. Before the star died, it blasted out a bunch of shells of material into the space around it. And so then when the star actually detonated as a supernova, this shock wave went out and compressed these shells and threw a lot of material out of the supernova into this surrounding previously sent out wreckage. And so you've got these really cool kind of twists and twirls in the nebula as this material is colliding together. It's a really fantastic image. And we're getting these all the time. I would say we get a new interesting image coming from JWST every 3 or 4 days that we are reporting on at Universe Today. And if you watch the Space Bites episodes that we do every week, we typically will cover them. Oh, Uranus. We got some new images from Uranus last week. So like last week we got Cass A and Uranus, and that's like 1 week. And so I would say that's the cycle. Now, JWST is taking a ton of pictures. It's taking multiple science targets pretty much every single day. In some cases, it's only being used for an hour. In other cases, it's working for an entire day on some target. And right now, most of these targets are being sent directly to the astronomers who requested the time on JWST. They're reviewing the images, the data that they acquired, and they will be able to write their science papers. But a lot of other stuff is just released publicly immediately as it's done. And there's a great community of amateur image processors, people like Judy Schmidt and others who watch as these data sources are filled with new images from JWST, and then they bring them into Photoshop and try to pull out the interesting image out of the astronomical data. So all the time, there's new pictures coming out. So, I mean, all I can say is, like, I highly recommend that you subscribe to this channel, because I will tell you every single time there's a cool new picture that comes out of JWST. Mage Matthews, where are we on the asteroid mining race? Who do you think will win? If there were to team up together, do you think the plausible process to make it happen would be? Where we are on the asteroid mining race is that anyone who starts an asteroid mining company goes out of business. That's where we are. There is no race. There is only going out of business. And that's because there's just no infrastructure. There's no viable way to get out to an asteroid, to survey, to find out what's there, to extract the resources that you require, and to bring them back to Earth or anything in any way or form that we can then use. There's nothing. And probably for the next couple of decades, it's going to be the same thing. we will see things start to change when there is some kind of space infrastructure, whether it is like a base on the moon where astronauts are harvesting local resources, or whether there is some kind of refueling in space or some kind of like 3D manufacturing or something that is using materials in space. So like there's a bunch of them. Like I could list off 5 or 6 companies that have gone out of business in the last decade because they tried to start a space mining business. And if you want to start a space mining business, that is a good way for you to lose all your money. But there will come a day when we have the infrastructure, when we are regularly going to space, when we are needing those kinds of resources in space, and the space mining companies will have their renaissance, and this time the industry will stick around. Jason D. Will the Kessler syndrome eventually lead to a coherent ring around the Earth, or will the satellites fall out of orbit before this can happen? So the Kessler syndrome is this theorized point where all of the space junk that is orbiting around the Earth crashes into each other and turns into smaller and smaller pieces, and eventually all you've got around the Earth is just this buzzing, whirling sphere of metal moving at 28,000 kilometers per hour. And you can imagine then any attempt to fly a spacecraft out of the Earth just passes through this grinder and just gets turned in dust and added to the space debris problem. And that's not exactly accurate. There are many different orbits. There's stuff that's low Earth orbit where you're just like say 500 kilometers above the surface of the Earth. There's orbits where you're like 1,000 kilometers above the surface of the Earth. And then you've got orbits where you are more than that, 2,000, as well as you're in geostationary orbit where you're like 35,000 kilometers away from the Earth. And each one of these orbits has a length of time that the material is going to remain in orbit before it re-enters the Earth's atmosphere. So the stuff that's down around 500 kilometers above the Earth, it's still interacting with the atmosphere that a spacecraft at that altitude will return to the Earth within just a couple of years. You get up to 1,000 kilometers, and now you're looking at like a couple of decades. And you get up to 2,000 kilometers, and now you're looking at a few hundred, if not a few thousand years. But the distances between the objects get bigger and bigger. And so the stuff that is in low Earth orbit is very close. The stuff that's in higher orbits is farther away from each other, and so on. And so you could imagine material sort of crashing into other material at a low orbit, but then that material is going to re-enter the Earth's atmosphere and really clean itself out. And so there's no way to maintain a debris sphere in low Earth orbit. It's the higher orbits where it's a bit of a problem. But then because of the increased space in between the objects, you're probably never going to get to this point where space is impassable. It's just that it's going to be a friction, that you're going to lose spacecraft from time to time because there's more and more space debris in that region. And you might get to a point where the risks to your spacecraft are so great that you're not willing to put a spacecraft into 1,000 kilometer orbit or a 2,000 kilometer orbit, that you're just not willing to pay the insurance costs when there's a 1 in 10 chance every year that your spacecraft is going to be destroyed by space debris. But we'll still be able to get out. We'll still be able to launch on our rocket, be able to fly through the region in just a few minutes and get out into deep space again. So really the risk is an increased ongoing expense for operating spacecraft within those orbital spheres. And so it will never turn into a coherent ring because the satellites are all in different orbits. Some are on polar orbits, some are in equatorial orbits, and they could collide with each other. And then the debris is going to go in different areas. And so you're going to have this debris in more of a cloud. But there will be some regions that are denser and have more debris. And so we may get to a point where if you want to have the safest exit from planet Earth, you take a flight trajectory that carries you, say, above the most dangerous parts of the Kessler cloud to get out into deep space. But let's hope we don't reach that point. Just clean up after yourselves, everybody. Mr. Monocle, it's a known fact that these galaxies are all moving away from each other at an accelerating speed. I was wondering, how big, how small does this phenomenon go? So the phenomenon you're talking about is dark energy, this idea that the expansion of the universe, or I guess the distances that are growing in between galaxy clusters, is accelerating. And you're exactly right. If you have two galaxy clusters that are far apart and they're already, say, 1 billion light years apart, and they are drifting away from each other with the leftover momentum from the Big Bang. They're also accelerating away from each other thanks to this repulsive dark energy force that is entering the universe and sort of pushing objects away from each other. But we know that dark energy isn't going to pull the Earth apart. It's not going to pull the solar system apart. It's not even going to pull the galaxy apart. So where is that line? And it is somewhere in between the sort of the local group size and the supercluster size. So we know that here in the Milky Way, we have the Andromeda Galaxy that's coming towards us. We know there's M33. There's all these other dwarf galaxies that are surrounding us. And this is the local group. And the local group is a part of a larger group of galaxies known as the Virgo supercluster. But we're not actually bound gravitationally to the other objects in the Virgo supercluster. They are moving away from us. We will never merge with those galaxies, and they are also accelerating away from us. And so there is this perfect balance point. Like, it's farther away than Andromeda, but it's closer than, I don't know, M87, right? Some galaxy. So somewhere in that gap, there's like the perfect place that if you plopped a galaxy there, it would drift towards the Milky Way and merge with Andromeda, the Milky Way, and M33. But if you were like a little farther away, then the expansive force of dark energy would carry it away, accelerating it away over the cosmic horizon, never to be seen again. And, you know, it is in the tens of millions of light years. So number is the distance to where you've got that balancing point between gravity pulling things together and dark energy pulling things apart. All right, those are all the questions that we had today. Thank you, everyone, for asking your questions in the YouTube comments. And thanks to everybody who showed up for the live show Monday, 5 p.m. Pacific time. All right, those are all the questions. Don't forget to vote, and we'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universe.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to David Gilton and Maud So, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.